Hello everyone, thanks for coming. Today we're going to do a review of our week 9th lecture of the ODE course. So in this week, we talked about how to apply the Laplace transform to solve second-order non-homogeneous ODEs, as well as some theoretical properties for ODEs. So first, we introduce the Heaviside function. The Heaviside function is also known as a step function because it is the simplest discontinuous function. So it has a jump discontinuity at some t equals to c. So what if the right-hand side for the non-homogeneous second-order linear ODE is discontinuous? Let's say it's a combination or linear combination of the Heaviside functions. So in this case, we need to be aware that even if G is discontinuous, Y and Y prime, they are continuous. It's just the highest order derivative, Y double prime, it may have jump discontinuities, as the jump discontinuities are at the same points as the external force G. So for higher order equations, the highest order derivative may have jumps, but lower order derivatives as a solution, they are still continuous. Specifically, for any piecewise constant functions, they can be written as a linear combination using the unit step or Heaviside functions. This is a very important property. We have the Laplace transform shifting theorems. The shifting theorems basically can help us get the Laplace transform, where the external force is a linear combination of the Heaviside functions multiplied by some other functions. We have the second shifting theorem. So this is a time shift, which means for the signal f, if we delay the time by c, then the Laplace transform of the delayed signal is e minus cs times the Laplace transform for the original f. Then we also have the first shifting theorem. So the first shifting theorem tells us if we magnify the signal f by some exponential growing factor ECT, then the Laplace transform of ECTF is the Laplace transform for the original function, but the argument is s minus c. So here, if the original Laplace transform exists for s greater than a, then the Laplace transform for ECT times small f exists for s greater than a plus c. So the interpretation is that if we multiply f by the exponential growing factors ECT in the time domain, then the Laplace transform would shift horizontally by s units in the s domain. So those two shifting theorems are very helpful if we apply the Laplace transform to solve second-order ODEs, where the right-hand side, they are discontinuous. Then we talked about the existence and uniqueness of solutions for first-order ODEs. Similarly, we also have very similar theorems for first-order ODE systems. So suppose we have the initial value problem. Our existence and uniqueness theorems tells us that if both f and the derivative for f are continuous in a rectangle, then there exists an interval for t in which the initial value problem has a unique solution. So the interval may be smaller than the rectangle for t. So h may be smaller than a here. So how to prove the existence and uniqueness theorem? So we are using the fixed point iteration theorem, which is called the Picard iteration. We assume there exists a solution. We plug this solution back to get the integral equation. And how do we find the solution? We set the initial guess phi 0 equals to 0, and then we use a Picard iteration to approximate the solution. Because both f and the derivative for f, they are continuous, then we may impose some uniform boundedness condition, we may get a convergence function series based on the Picard iteration. So here, h, the interval on which the solution exists, may be smaller than the original a. This is because we may first impose some uniform bound for both f and its derivative. And then, in this sense, we need to ensure that all members of the sequence exist. So the proof is technical, and you can try to do this as an exercise. You can try to prove that the sequence would converge uniformly by the Cauchy convergence theorem. There exists a limit function, and then you can prove that the limit function satisfies this integral equation. Because it satisfies this integral equation, then if we take the derivative, of course the derivative exists and equals to f of s and phi. Therefore, phi solves the original ODE. By using the comparison principle, you can also prove that the solution is unique. Therefore, this is a sketch of the proof for the existence and uniqueness. Basically, the existence is using the Picard iteration. Uniqueness is based on the fact that the derivative for f is Laplace continuous on y. Of course, if f is continuous on y but not Laplace continuous, then the solution might not be unique. This would be another story. Thanks for listening.